circuit, resistor, inductor, capacitor, circuit. Series today, parallel on Thursday, and then we will be done. So before we get into that, last time we did the parallel RL circuit. So for that one, when we were going through to find our impedance, we had this equation here for our magnitude and our angle, which we can then go through and do trig to break that into the different types of coordinates, or if we wanted to. So depending on what our goal was, we were able to go through and again be able to use the polar versus the rectangular form. And if we had to go through and do combination RL circuits, same process as RC. So going through flipping things back and forth between series and parallel to go through and eventually combine it all into one. So any questions from last time? So today we're going to go through and we are going to do talk about some RLC circuit stuff from this textbook. Not everything that in this textbook is what we are expected to be able to do based off of the course competencies. So we will be visiting the previous textbook. In particular, this is chapter 8, section 4. The section or the textbook name is that on that first page of the packet, and all of the super relevant information you need from that will either be in these slides or is attached as a very blurry table in the packet itself. So you don't need to go get this textbook. I have a very crappy PDF, so I'm not going to share that with you either. So today, again, we're just doing parallel or series. Everything is just in row. Technically, it doesn't have to be in this order, but it's almost always just graphically represented where we have a resistor, an inductor, and a capacitor in the order of the letters of RLC to go through and have them in series. So let's think about kind of how we've been dealing with the RL and the RC circuit. We were going through and we were dealing with things in the real and imaginary planes. Which circuit component or components was real? Which one did not have the J?
The resistor.
What about the inductor, real or imaginary? What about the capacitor?
Same, imaginary.
These were both imaginary. So these had the J terms. And in particular, if we were thinking about the equations associated with them, did we just use inductance and capacitance as given? What did we have to use instead? So we had for XL, that was our 2 pi frequency times the inductance. And then we had XC, 1 over 2 pi FC for that. So now that they're in series here, what do we think is true about the frequency in both of these equations?
They're the same.
Yep, should have the same frequency for both. So what's going to start happening is as we go through and explore things today, we're going to be looking at our impedance once again. So we'll have our real resistance part. And then we have something a little bit more complicated where we have our imaginary portion. But instead of talking about it in terms of XL or XC, we typically see X total. Where this is going to go through and be the absolute value of XL minus XC. Do you technically use the absolute value part? It kind of depends on what exactly you're looking at for your textbook. So for this one, we'll be seeing that absolute value of the two of them subtracted from each other. What you will then see is an extra piece of terminology used inside of the information about the circuit. So what you will see is that if the reactance of the inductor is larger than the reactance of the conductor, you'll see that the circuit is going to be defined as predominantly inductive. So this means that the inductor portion is more powerful in comparison to the capacitive portion of the circuit. Because what's going to be going on with these is the inductor, it's now fighting not only the alternating source, but it's going to be fighting the parallel plate capacitor charging and discharging. So it's fighting changing current on both ends. So if it's primarily inductive, the inductor part is going to play that larger role in going through and describing how the circuit is going to behave. If instead the capacitance reactance is greater than the inductance or the inductance reactance, you have predominantly a capacitive circuit. So it would act more like an RC circuit, even though technically it's not quite exactly the same. So there will be an extra piece of terminology that sometimes gets added to our questions to go through and tell us which way the circuit is behaving or like. So with this, right, we want to go through and talk about what does impedance look like? How do we have that in rectangular versus polar? But before we do that, any questions so far? So when we're talking about it in rectangular form, we're typically not going to see that absolute value inside of it. And the reason for this is we want to make sure we understand if we are going to have that, if it's going to look more like inductance or capacitance controlled circuit. You also see it sometimes represented as R plus J, XL minus XC. How did we find polar form previously?
Just use Pythagorean theorem.
What do you think we do with Pythagorean theorem once we have three terms in this particular case? Do I just square all the terms and then add them together, or do I need to do something first? Am I gonna, sorry, let me rephrase. Am I gonna have R squared plus XL squared plus XC squared? Or am I gonna have R squared plus this squared?
That's gonna be plus that squared.
Why do you assume that?
This makes more sense mathematically.
Yeah, so you are gonna see it where it's the real stuff squared plus the imaginary part squared. It is only in the inverse tangent part where we see the X total part. And again, that is going through and having XL minus XC. So you'll go through, if it's for like the RC circuit, RC will be larger. It will point the reactance, or sorry, the impedance will point in the negative imaginary direction. If it's for like the RL circuit, so predominantly inductive, it'll be a positive number. It'll pop it into the first quadrant. You'll have a positive angle. So this will go through, it gets us our impedance. And once we have impedance, we can go through and we would be able to take our circuit and treat the impedance value like we would any sort of resistor. Kind of how we've done the past couple of weeks, as well as what we did with every other resistor ever. Is that necessary? We'll talk about that more so on Thursday, but no, that's what we can do. We can also go through and talk about, right, we've talked a little bit about lagging and leading. And with the RLC circuit, especially those in series, again, depending on if XL or XC is greater, is going to determine how that lagging and leading is going to work out. So for example, if the circuit appears inductive, so again, that is XL greater than XC, the current is going to lag behind the voltage. And because they're in series, they all will share the same current. So now the voltage is going to lag. What do you guys think if the circuit is going to appear capacitive? Do you think the current is also going to lag, or do you think it's going to lead?
Lead.
Yep, they are opposite behaviors on what is going through and happening. So this is going to give rise to a lot of different situations, right? Because we can have, in reality, if we have XL and we have XC, there's three different situations that we can have. We can have the greater than or less than parts. So if we're talking about XL, it can be greater than or less than XC. Those are the two types that we've talked about so far. And with going through and doing that, those are going to give us the appears inductive, appears capacitive, whatever slight variation you want to call it, predominantly inductive, predominantly capacitive, and the behaviors are going to look different. We can also look at the case where XL is equal to XC. And we'll get to that a little bit over the next couple of slides. We want to explore what do these differences actually represent. And as we go through and work through the stuff from this textbook, we're not going to really be worrying about where the math is coming from. When we go through after our first example and we start kind of getting in a little bit into the math, we'll talk about why we're doing what we're doing, but it will not be something you are expected to be able to do from scratch. So we're going to see a graph on the next slide, and we will get to that math a little bit here later in lecture. So any questions so far? Okay, sorry. We're doing an example. Sorry, I forgot I moved this. We're gonna do an example, and then we're gonna talk about the graph. So we are going to do whatever number this happens to be. I cut that off. We're gonna go ahead and do that. So I need to, before we go anywhere, right, we're looking for the impedance in polar form. So I need to worry about units. All right, where do we want to start?
The inductor.
Okay. 1 millihenry is how many Henry?
0.001.
Or -3, whatever. What about capacitance? I got picofarads here. Pico is 10 to the what? Positive 12? Negative 12. If we had a 10 to the positive 12 farad capacitor, I do actively believe that would cause great harm. All right. Problem. What's the problem that we have here? All right, at the end of the day, I want to find Z. In particular, right, I'm looking for the polar form. So I'm gonna need the square root of R squared plus XL minus XC squared. What problem do I currently have? Getting to this point where I can start solving for polar.
So the two reactants.
Okay. What's the problem with that? I don't have a frequency. Why does the textbook not give us a frequency? I don't know. But here we are, so we can either give ourselves a nice frequency or we can give ourselves a not so nice frequency. What do you guys want to do? Okay, so what do I want to use? One, okay. We're gonna say our frequency is 1 kilohertz, or how many hertz? 1,000 hertz. Okay. So we get to go through and we are gonna do it. So what do we do now? Okay. So we gotta do our reactants. Or, yeah, so we'll have XL 2 pi FL 2 pi times 1,000 hertz times L 1 times 10 to the negative 3 Henry. So we'll have 2 pi 1,000 times 1 over 1,000, so we should just end up with 2 pi. XC will have 1 over 2 pi frequency times capacitance, so 1 over 2 pi 1,000 hertz over 47 times 10 to the negative 12, or yeah, farads. This one I can't do in my head. What is this? Yeah, that's when you have a picofarad.
Not including the pi, it's 106. Right. 106,38297.
Pi. Again, you do whatever you want for you doing your math. So now that we have these numbers, we are ready to go through and solve. Also, in case you were curious, this is sorry, this was number. Sorry, it's just this, it's the circuit from 10. But it's not. I think I might have typed that wrong. It should be 10. We're not quite doing 10. Well, 10-ish. The reason it's 10-ish is if we're looking at 10, it says at the resonant frequency. We're not doing it at the resonant frequency. That's okay. All right, so now that I have all of these unhealthy values, all right, we're gonna go through and plug them in here. Did I need to do anything with my resistance value? So we're gonna have 220 ohms. I'm gonna drop the ohms on that. I'm gonna have 2 pi minus that. I'm gonna drop the decimals on that large number there, because they won't matter. Taking a wild guess. Some of these numbers. This is gonna basically show up as almost exactly this number. Again, right, so we'll minus 2 off this. Oh, I need to square. Right, then we then square it and add 220 squared, which is small compared to that squared. So I'm gonna take a wild guess that Z is gonna pop out as approximately 1.06, or no. Sorry, I'm trying to. It's gonna be close to this, but we should probably plug in the pi. Should have grabbed my calculator. 1.06 38298. So we should get something about 3.34 times 10 to the 7 ohms. Ish. Again, I'm gonna actually plug this in. I just know that that number's really big, so it's gonna dominate everything. For our angle, it's still the inverse tangent, but now because it's x total, that's gonna be XL minus XC over the resistance. This should give us the closest thing to 90 degrees that's not legally 90 degrees possible. Such that I'm guessing the calculator will tell us that this is not negative 90 degrees. So 3.34 times 10 to the 7, negative 90 degrees ohms. So because of the frequency we have chosen, is this inductive or capacitive? It is capacitive. How do we know? Last I checked, 2 is less than this number. So there's not a lot of actual interesting parallel RLC circuits if we're doing it at this level. So this is how you would go through and just do it. I would give you frequency if that is something that you need. Any questions on 10-ish? Again, not technically question 10. So now we'll talk about the graph. And again, don't worry about the math. We will get there soon. So in this graph here, on our x-axis, we have the frequency. On the y-axis, we have the reactance. And we basically split this into 3 different parts. We're going to have a region where we have the capacitive behavior. We have a region where we have the inductive behavior, and we have a nice little straight line, which is that solid portion there. So with this curved line, this is our XC. So because it's 1 over 2 pi frequency times capacitance, as that frequency changes, it looks like 1 over X. With XL, it is solid because it's 2 pi frequency times the inductance. So 2 pi frequency is our slope for that. If we look at the graph, there is one very special point where the 2 lines are going to meet. That is going to be where XL is equal to XC. So these are, again, it's the 3 different things that are dominating our series RLC circuit. So let's say we have a really low frequency. So we're somewhere down over here. Now we want to think about what would our series RLC circuit do with a low frequency, right? Frequency being smaller when we're just multiplying by that value. We're going to get a smaller value. We're dividing by a small number. We get bigger numbers. So for low frequencies, XC is high and XL is considered low. So that's basically comparing this lighter line compared to this dark one here. So at low frequencies, which is anything that happens over here, and that will be circuit dependent. That is going to be where XC is greater than XL. That is our capacitive circuit space. If we look at high frequencies, which is everything else over here, what do you think this is going to correspond to? Reactance or inductive or capacitive, like what line is higher? Inductive. This is going to be where XL is greater than XC, and we have an inductive circuit. If we think about what we're doing here, to go through and figure out which one is more controlling, we're looking at XL minus XC. What happens when the curve and the line cross, when XC and XL cross, what should they, if I plug them into this equation here, what should that get me equal to?
Sure.
So at this particular point, the reactances between the capacitor and the inductor are going to cancel out. And what this is going to do is if we wanted to go through and look at impedance, it would just be the resistor. And we're going to come back to this in a little bit here, but it is sometimes referred to as the series resonance. It is a very specific frequency that is circuit dependent because, right, it's going to depend on what is our frequency, the inductance, and the capacitive values. So we will get to that in a couple of slides from now. So these are the three different situations that we can have. Right, we can have capacitive, inductive, or we can have where we have a reactance cancel out, and we essentially go back to having a resistive circuit. When we go through and look at mathematically where some of this comes from, this is going to give us our three different types of damping. So it is relevant to going through and seeing the math, but everything that we do for RLC, so both series and parallel, always gets broken down into three different typings. Any questions so far? So with the RLC series situation, the capacitor and the inductor are always going to be 180 degrees out of phase with each other. So if we go back to thinking about our phasor diagrams, for the resistance value, right, that's always just kind of been along that real portion, it's just going to be there. If we're thinking about our capacitor, which we dealt with next, that was down here, that's going to be our XC. And then for the inductor, it's going to point up here, XL 180 degrees with respect to to one another. So this is gonna be interesting if we go through and think about the voltages then. Because if they're in series, they have the same current. Not that the capacitor doesn't technically have current going through it explicitly, but right, it's contributing the same. But the voltage thing's gonna be a little bit weird. So let's look at some, again, just a standard series RLC circuit. We have a resistor, it's doing resistor things, it's just passively existing. With the capacitor and the inductor here, they are out of phase. So I wouldn't simply just go through and add the different values together. I'm going to have to subtract one from the other. In particular, the voltage across the inductor and the capacitor is always less than the individual components. So because they're pointing in opposite directions, because of how they're interacting with the rest of the circuit, one of them has to get subtracted out. There are rules to it, but for the sake of this class, they are not super duper important. We're acknowledging it, and then we're not going to see it pop up when we see our math shortly. You can go through, and if you were to plot out the voltages for the inductor and the capacitor over time via superposition. So you can do superposition outside of doing sources. Here we're superimposing our waves, basically just adding those waves together. We can see that for the capacitor, which is this bottom line here, compared to the inductor, individually, they have different values, but when you sum them together, it ends up being a smaller overall voltage. It's just a fun little weird thing that pops out. You'll see this pops up a couple times in the text, but we're not going to do anything with it. Any questions about series RLC voltage? All right, so let's talk about series resonance. XL equals XC. It occurs at one frequency for that particular circuit. As we go through and look at it, basically what we have here is, because these are equal, and if we go through and think about our equation for C, right, that's R plus J XL minus XC. That term ends up being 0. So really ZT is just equal to the resistor, and we don't have to go through and worry about it much. How would we find what this frequency value is? What would I need to go through and do? What's the equation for XC?
By frequency times capacitance.
And if that is equal to XL, which is 1 or 2 pi frequency times inductance, how can I go through and solve for frequency?
Of the denominator
Mm-hmm.
and over to the second one, so you get F squared and then
Yeah.
divide everything else.
So you'll have, sorry, have 4 pi squared F squared LC equals 1, or frequency is equal to this. Depending on who you are as a person, depends on how you like to see this written out. Because you have 1 over, so some people like to have it all in the square root, some people don't. Typically, you'll see it as 1 over 2 pi, square root 1 over L times. And this frequency is very important. It has its own special little name, where it is in particular, I remember what it's actually is. I always mix it up with the other one. It is related to what is referred to as resonant radiant frequency, which we'll talk about here in a little bit. Any questions about series resonance so far? So you can go through and you can plot all of this out associated with the voltages. So here we have one instance where our voltages, we have a positive voltage for the capacitor, a negative voltage for the inductor. If we were to go through and sum them out or sum them together, because they are 180 degrees out of phase, they'll sum up to 0. Same thing is true when the capacitor is negative and the voltage is, the inductor is positive, right? That goes through and has the different ones there. Both sum up to 0, 180 degrees out of phase. So, bunch of different ways you can go through and solve for that. Any questions so far? We just did this, so I'm not gonna do it again. Technically with the FR, or it's sometimes given the subscript R there to indicate it's the resonant frequency for the sake of doing that. So if we were to go back and do the actual problem for chapter 17, number 10, we would need to first calculate this frequency, then go through and use that to solve. And by use that to solve, I really mean use R. So look, again, 10 is a little bit different with that. So we are going to get into a little bit of the hardcore math portion of it. So are there any questions on conceptually what is going on with the RLC circuit so far? So before we get any further into the math, I want to just, again, set expectations for what we are going to be doing. We are going to be looking at solving this equation here. However, in order to go through and solve this, we need to know a lot more about what is going on with our individual circuit, and it requires us to understand second order differential equations, in which that's not a requirement for this class. So I'm going to show you what it looks like. We're going to talk about what mathematically would need to happen to get to those results, and then we're going to talk about the results. If you look, I forget what pages they're on, in the packet, I know one's on the last page and one's like kind of halfway through the packet. I have the table, I know it's a little blurry, the table of all of the results for the solutions. One of them's labeled parallel, one of them is labeled series. As long as you can figure out the frequency calculations and then match that to the type of solution that we have and plug and chug and go through that, I am perfectly happy with it. You are not hand solving a second order differential equation for this class. But it's important to understand why the solutions look the way that they do. So before we get into that, are there any questions about the expectations for the math? All right, so let's talk about the circuit and we'll talk about the equation here for it. So here we have a circuit. This is another set of, we have a resistor, an inductor, and we have a parallel plate capacitor. The reason it's curved is to just numerically would have to be a specific value. So again, sometimes you see them curved. Kirchhoff's voltage law, or Kirchhoff's loop law, whatever version of it you want to call it, always applies, which states that the sum of the voltage as we go around the loop has to sum up to 0. So if we look at our first term here, Ri, this is Ohm's law. Or I here is an instantaneous current, so I have the voltage across my resistor. This middle term here, I have the definition for voltage across an inductor. L times the time derivative of my current. And then I have the voltage across my parallel plate capacitor, which is V over C, or sorry, Q over C. And with that Q, if we look at the definition of charge, it's equal to the time integral of the current. As it stands right now, mathematically, this would be an absolute nightmare to go through and solve. So what's typically done is we want to make everything be a derivative. So in order to get rid of, so if we think about like integrals and derivatives, similar to how we think about multiplication and division or addition and subtraction, they're opposites of each other. So to get rid of this integral, I need to make sure I would need to take the time derivative of it, but I would have to do that to every term that I have. So I'm going to need to take the time derivative of my resistance term, the time derivative for the voltage across my inductor, and I need to take the time derivative of 0, but that's still just going to be 0. So that's going to put it into the form of the second order differential equation. So with this second order differential equation here, it is named as such because I have a second derivative inside of it. If we think back to when we just had the capacitor or just had the inductor, technically those were first order differential equations where we only had one time derivative inside of them. Here we have a second order because we have a double time derivative on one of our terms. Now, when we see, and this is just a weird mathematical thing that I think a lot of people like to do, for going through and rearranging second order in particular differential equations is typically you want to have no constants associated with a second order term. So if we look at our original equation that had a time derivative in it, that has become our second order or second time derivative. So we need to get rid of the inductance. So we divide all the other terms by L, making it such that our terms are the second time derivative of the current plus the resistance over the inductance times the time derivative of the current plus current divided by inductance times capacitance. And if we were able to go through and solve this, when I plug in the equation for current, I go through and take these time derivatives, they need to sum up to 0. That is the way you go through and get the solution is that whatever equation I have for I, if I plug it in here, they need to sum up to 0. If you guys want to see the proof, I'm happy to go over it tomorrow. But with as we've seen a little bit already in lecture today, we've seen that depending on the values of the frequency, that's gonna change how the circuit behaves in terms of being inductive or capacitive. Which means that if we were to try to go through and solve this particular second order differential equation, we're gonna end up with 3 different solutions depending on if our circuit is more inductive or capacitive, or if we're at the situation where it's essentially resistive, and we have that series resonance. So a couple more things we need to see in order to go through and just talk about how the solutions are represented. But are there any questions so far on what we're doing? Yes.
You divided by L to get rid of the constant, but if this is there, still a constant, what is that just?
I get rid of it on the term that's the second, that has the double derivative. So I still have constants, I can't get rid of them ever,
Yeah,
but it's typically represented where this one doesn't have any constants. That is a weird philosophical math problem, not an engineering choice. So in differential equations, you almost always go through and rearrange it such that the second, whatever term has the double derivative in it, that one has no other things. Any other questions so far? So this is the same equation. What tends to happen is writing this out can look a little intimidating, especially if you haven't seen differential equations recently or in a while. So sometimes what you go through and do is you'll see something represented with what is referred to as the characteristic equation, which of course, for some reason, we just use S for that. So where I have the double time derivative, it's S squared. Or I have a single time derivative, it is S. And here, I don't have any time derivatives. I don't have any S's in this term. And the idea of going through and doing this is that we want to figure out how can we start solving, again, this second order differential equation up here. And again, this is something that's more so for RLC circuits, which are more complicated than the first second order differential equation you'll do in that class. S is a little bit of a mess. It has 2 solutions. Why does it have 2 solutions? Well, we have a square root. And so because we have this square root, you can do plus or minus with it. And in general, the characteristic equation 1 is going to happen when we do the positive. We're going to take negative r over 2l plus the square root stuff. And 2 would occur for the minus part. And again, engineers, it's not just engineers, it's really just anybody who has to write the same stuff out multiple times, gets lazy. And so instead of writing out all of these terms every time, we see that they're replaced with alpha and omega naught, where alpha is referred to as the Neper frequency. This is one of the frequencies. So it's not the frequency of the source, but it is one of the frequencies that is going to tell us what type of damping we're going to have in our circuit. Talk about damping a little bit more on the next slide. So with this here is one of the controlling things that we have. And it's basically so that we don't have to write out R over 2L over and over and over again. So it shows up a lot. The 1 over LC is our resident radiant radian frequency. And if we look at it, you can see that the equation's not quite exactly the same as what we have. So it's 1 over the square root of LC, which means that the reason it's done this way is a little bit cosmetic, but it makes it such that we have alpha squared and omega naught squared. So those would be positive numbers being put into the square root, even though we still have a subtraction in there. So a lot of formulas, I understand. I promise you, they have. But with this, with the characteristic equation, again, it's the reason we go through and write it out this way is to help us go through and start taking our particular circuit and getting a solution specific to that circuit. The idea of using S1 and S2 is that I don't have to write it out every single time. So it is a simplification step for going through and writing out the solutions. It's just going through and making it such that actually doing the second order differential equation stuff in theory is easier. With the two frequencies here, we can go through and utilize those to help us figure out what is going to go on in our circuit over a long period of time. And again, long period of time. So before we get into what is damping, what are our solutions going to start looking like, we want to talk about why we have 3. So do you guys think it's possible that we can make it in this square root such that we're going to get a real value? Like there's some sort of resistor, inductor, capacitor value such that the square root is real. If you had to guess. Yeah, we're going to be able to find a real solution. Do you guys think we can find an imaginary solution? Is 1 over, sorry, right, because it's minus, is 1 over LC ever going to be bigger than the R over 2L quantity squared? Right, we have 3 different types of behavior for our series RLC circuit. It's all coming from this square root here. So we can have a real solution. So the square root is a positive value. We can have imaginary, where the square root is going to be negative. And we can also have the one where the square root is going to be equal to 0. We have 3 different solutions, 3 different types of behavior our circuit can have. So we're going to go back and slide a little bit because I forgot to put the circuit on the next slide. And we want to talk about what is going on. But before we do that, any questions so far on kind of what we've been, right? This is a bunch of terminology, but anything so far? So let's talk about this circuit. If we just had a resistor circuit and we talked about the parallel plate capacitor, what did it do as time went on? Let's say it was fully charged. We closed the circuit. Again, we're ignoring the inductor. What happened over as time passed? What happened to the current?
Slowly decreased.
Yeah, decreased, and it decreased exponentially. We had that nice little curve. We had the 5 tau to tell us when that capacitor was fully discharged. What about if we ignore the capacitor? What happened after a long period of time when we had an inductor resistor circuit? What happened to the current?
That increased,
After a long period of time? It's just the resistor and the inductor. They either both increase or both decrease for the RL.
current gonna flatline at some point.
It flatlines and eventually will flatline at zero. They both exponentially decreased over long periods of time when it was just the resistor and either the capacitor or the inductor. So if we think about what's going to happen in this situation here, typically we say the capacitor is charged, we close the switch. What that's going to do is over time, this is going to discharge, and the inductor is going to counteract the constantly changing current. Depending on if the inductor or the capacitor is stronger, is going to determine how is that circuit current going to behave over time. And that leads us into the concept of damping. Eventually, this is just going to be three random circuit components with no current, no voltage in it. But we want to understand how does it get to that point. And so that's going to be where we have damping. So here we have the three different types of damping, and I'll roughly plot what these look like here in a second. But we have what's referred to as overdamped, underdamped, and critically damped. This is a type of motion for any sort, or sorry, this terminology is for any sort of object that is going to oscillate. You have it for springs. So the door in the classroom here, it technically has a damper at the top of the door. And it is designed such that the door is just going to slowly close. Right? It's not going to close and then open and then close again, right? It just closes. If we think about shocks on a car, let's say you hit one of the many potholes that has grown over the past week, right? You hit that, depending on if the shocks in your car are good or not, they're going to depend on how fast your car is going to go back down into just kind of being in that standard situation. So if we look at it, those are the three types of damping. Again, I'll talk about those in a second. Here we have the relationship between the neper and the resonant frequency. And then on the right, the typed versions of the solutions that are on the next slide. Talk about in a little bit. So depending on the relationship of our frequencies, that is going to determine what our solution looks like, which is going to determine how our function goes to zero. All right, so let's look at how this typically is represented. We have time, and in these equations here, they are voltage based, instantaneous voltages, technically. If we look at the critically damped case, this is the nicest possible case. This is what you typically want a lot of your things to go back to equilibrium to look like. So what that will go through and look at is critically damped. It is never going to oscillate. It just starts in positive or negative voltage and it just goes down to zero after some amount of time. No time constants here, but it would just go down and do that. We can see that that's going to be the case based off of the two negative exponentials we have here. With over and under damped, they, over damped, not fun. For over damped, right, we have two positive exponentials. But because of how S works, they're gonna have different numerical values. And for the over damped case, over damped, by the way, is sometimes called, strong damping. I don't know why, but for that one, it's going to a long period of time later, get down to zero. So it too is never gonna oscillate, but it takes a long time. And then we have the underdamped. Where underdamped is kind of doing its own thing. It's gonna oscillate back and forth, eventually reaching zero. So with the cosine and the sine term, that's gonna go through and give us our oscillation. The negative exponential part gives us what's referred to as the envelope, which is going to shrink it as time goes on. So depending on the relationship between resistor, capacitor, and inductor, it tells us how eventually the circuit voltage and current will go to zero. Let's talk about, or if are there any questions, and then we'll talk about the equations. I will give you this table for the final. You do not need to memorize it. What you need to be able to do is go, boy, howdy, I sure know my resistor, so my resistance, my inductance, and my capacitance, and I have converted them all into their base unit. You go through, you do that, you're gonna get alpha, and you're gonna get your omega value. You're then gonna go through, and you're gonna square both terms. I don't know why you square both terms, you should be able to tell from now. But you're gonna look, is alpha squared greater than, less than, or equal to omega naught squared? It's my Neper frequency, less than, or greater than, less than, or equal to my resonant frequency. Once you figure that out, if alpha is greater than omega naught, you're gonna go, boy howdy, that's overdamped. And you're gonna look at this part of the table and this part of the table only. This I here is my equation for current. We have that. We are given the relationship that A1 plus A2 is equal to the initial current for my system. And then we have an equation down here that tells us that the time derivative for our current is equal to S1A1 plus S2A2, which simplifies down to 1 over L minus our initial current minus V naught. So for overdamped, you have to have some information about that initial current value, and then you are able to go through and solve. If you have overdamped, what you're going to go through and do, right? That's where alpha squared is less than omega naught squared. You're going to go through, boy howdy, I have this ugly equation here for current. At time is equal to zero, which is what this is indicating. The plus here is to indicate that the switch is closing at time is equal to zero. V1 is equal to my initial current. And if I do the time derivative part, I'm going to have a relationship that I can then use to go through to find V2, figure some stuff out to plug it in. If we have critically damped, we have our equation here. At when the switch closes, D2 is equal to the initial current. And again, we're able to go through and use the equations to solve. So again, what you're gonna need to go through, do, calculate both of your frequencies, figure out what type of equation or what type of solution you should be using. If you calculate the two of them and tell me, because A is gonna be, tell me what type of circuit do you have, that is gonna be 5 points. If you write down the correct current equation from that, boy, howdy, you just got 3 more points. Everything beyond that, right? So that's 8 out of the 15 points that this is gonna be on the final. So at least get to that part, even if you're uncomfortable going through and doing the rest of the solving. At the end of the day, if you look at the packet, if you can do those examples in the packet, you are ready for the question that will be on the final. I'm not gonna try to trick you with going through and doing anything. Just gonna go through and you follow this table and do some algebra, which I believe you can do. So we're gonna start, but possibly not finish 41. So are there, chapter 841, so for the other textbook, are there any questions before we do that? So this one, we're still gonna use some information from the previous table, but it's a little bit awkward on kind of what it is. So we have a circuit, we're given some pieces of information and we gotta go through and we've gotta solve the rest. It's fine, we can do that. So with this one here, it's a little bit weird because it gives us the equation. And so we want to establish what equation does this look like? So we're gonna look at our table and we're gonna go, boy, howdy, only one of the equations has cosine and sine in it, and that has to be what?
Underdamped.
Boom, we are underdamped. How would we check if this is the correct equation or not?
Calculate your two frequencies and see which one's
Mhm.
your square, and which one is greater.
Yep. We could go through and we can figure out if alpha squared is less than omega naught squared. We technically have that ability. We can talk about it here in a second, but we could prove it if absolutely necessary. All right, so, right, we've gone over the fact that we were given this ugly equation. What other information are we given in the text of the question? What is this 80 nanofarads? What should I probably do with that?
It's not even.
Nano is 10 to the what? Cool. What is this 7.5 milliamps? Represented by capital I naught. We don't really, we can convert it if we want to. We could also hold off on it. It's all kind of gonna be dependent on what we wanna go through and do. So we'll get there. We'll just talk about it in a second. What's this negative 30 volts?
Actual voltage on the capacitor.
All right, so that's what we're given. And then we're being asked to solve for resistance, inductance, B1 and B2. Basically all of the unknowns in our equation. So before we get anywhere, we're going to want to go through and look at what do we have to go through and start figuring out how can we solve for these other pieces. So I'm just going to rewrite the equation. I is equal to B1 e to the minus 2000 t cosine of 1,500 T plus B2 e to the minus 2,000 T sine 1,500 T. I don't care that time is greater than 0. That just tells me that the switch has been closed and I can go through and look at this. What I want to go through and do is I want to compare the equation that I'm given compared to the base form of the equation. So it's given, this is based, or the base form, which is I is equal to B1 e to the minus alpha t cosine omega d t plus B2 e to the minus alpha t sine omega d t. Right, those are comparing the two equations to each other based on the fact that this is underdamped. So just looking at this here, are there alpha is equal to what? I compare my two equations, what is alpha equal to?
2,000.
It's going to be 2,000. In particular, that's positive 2,000. We want to make sure that we have that. What is omega d equal to according to the equation? So that's by just looking at the equation. I now have my network frequency and I have this omega d. Well, what's omega d? Well, let's go back and let's look at it. So there's nothing here with omega d's base equation in underdamped. So if I go up here and I look at the never resonant and damped frequencies, I see the definition of omega d. It's going to be equal to the square root of omega naught squared minus alpha squared. So this equation here is for underdamped only. The only place we're going to see omega d, which means this is equal to the square root of omega naught squared minus alpha squared. Any questions so far? So let's solve for the inductance and let's solve for the resistance. And that's probably going to be all that we have for time. So to solve for resistance, what equation might be useful? Again, we go through and look at this. We want to solve where's a resistance showing up in the case of our frequencies. There, so it's only showing up in the alpha one. Do I have L? No. But I am going to need that equation. So we're just going to write that down. Alpha is equal to R over 2L. Which means that I need to use an equation that's going to get me to find the inductance first. Again, we're going to look at this and we're going to look at our frequencies. That's kind of what we have based on our equation. Do I have an equation that I can kind of currently, or based on the information that I have, get to solve for the inductance?
Omega naught.
Yes, I need omega naught, which I can find from omega d. Get omega naught, solve for L, to solve for R. Which we don't have time to do, so we're just going to write out one equation, or this. Omega naught is equal to 1 over square root of LC. Or omega naught squared is equal to 1 over LC. The reason I might want to have it be squared is if I look at my omega D equation, I have an omega naught squared, so I can just solve for that. So how would I solve for omega naught squared? And then we'll be done. It's the opposite of a square root.
Square.
I'm gonna take my 1500, I'm gonna square it, and then what do I need to do to the alpha squared? Which we have alpha, we can find omega naught squared, right? We'll have our 1500 squared plus 2000 squared. That'll give us our omega naught, which we can then go through, rearrange for L, get the value, plug it in, get the resistor, and then we can figure out the rest. But we will do that at the start of next lecture. Are there any questions on series RLC circuits so far?
Like the A1, B1, all those E2s, are those just constants?
Yes. It'll be constants based on the currents.